In this video, I'll show you how to determine if your March Madness bracket has a chance, however small, to beat any other bracket. Then, I'll delve into a mathematical proof that this method works. Hi, I'm Win928er. Let's get right into it. Take a look at this 8-team bracket where the first round has already been played. Here are two predictions of the tournament, A and B. They get points for correctly predicting results in the tournament. Green team names indicate that they predicted the game correctly. Red means they predicted incorrectly. And yellow means they could still be right or wrong depending how the tournament plays out. As you can see, B is performing much better than A. B has a higher score and a higher max possible score than A. But the question is it still possible for A to beat B? A's max score is still higher than B's current score, so you might think that it must be possible for A to win if everything goes just right. However, A only has one more chance to gain points, this game right here. If A's prediction is right and the Gammas win, B gets the additional points as well. That means A cannot possibly win, but how can we know in general? I'll show you the answer in just a moment, but for any of my mathematically inclined viewers, I encourage you to try this problem on your own. This is a good one, so give it a go. We need to make some assumptions about how the bracket scoring system works. First of all, we assume that an incorrect prediction makes no change to your score. This means you don't lose points for getting a prediction wrong. Secondly, each game prediction is worth the same amount of points for each bracket. This means each game in the tournament has one associated point value. All the major scoring systems for March Madness follow these assumptions. The typical scoring system looks like this. Games in later rounds are worth double the previous round. I will use this system for the examples in this video. But the algorithm also works for other scoring methods, like this reverse point system where the final game is worth the least. Also for this cursed one, and for this system where only the final game matters, which is how real March Madness feels a lot of the time. Alright, I'll show you the solution with these example brackets. To see if A can beat B, first imagine that everything goes A's way. All their picks win in every match. We ignore games which don't give A points. Then, we just compare A and B's scores in this situation. A's score will just be their max possible score, since all of their remaining picks won. B's score you'll have to calculate manually. If A's is higher, then it is possible for A to win. If B's is higher, then it is mathematically impossible for A to beat B. This procedure should make some sense. If it's possible for A to win, they ought to be able to win when everything goes their way. So we should only have to see if A has more points when everything goes right, which is exactly what you do in this algorithm. This process is a little tedious, but totally doable for a full-size March Madness bracket. Certainly much easier than simulating every single possible ending to the tournament. In the remainder of this video, I will show off a proof that this algorithm always works. First, we'll define some useful notation. We'll want to talk about the results of the tournament so far, so we'll denote this with the letter R. A bracket's current score is entirely dependent on the results of the tournament, so we'll define a function score sub A of R to talk about A's score at R. Similarly, we'll define max sub A of R as the highest possible score A can still get given the results R. It's worth talking a bit about what R actually is. We can view R as a set of individual game results of the tournament. If we index the games like so, an element of R would look something like Gamma wins game 1B. R cannot contain impossible situations, like a team winning a game they are not in, or winning a game in which their opponent has not yet been decided. Already, we have some useful properties. If a set of results S is contained in another set R, we can think of R as coming after S. You cannot lose points as the tournament goes on, so the more results always means a bracket's score increases or stays the same. Secondly, we can think of A's score as the sum of how many points they've gotten for each individual game result. A gets 0 points for each wrong prediction, and that game's positive associated value for each correct prediction. From these two properties, it follows that A's score at R is equal to A's score at S, plus A's reward for each individual game in R, but not in S. Continuing on, we'll want to talk about A's best case from R, which is the set of results containing R, and the additional possible results which give A points. Notice that A's score at A's best case is always equal to their max possible score under R, since all of their picks after R occurred. Any additional games after A's best case occurs can't possibly give A more points. So we have that any T containing A's best case gives A the same score as their best case. Similarly, we can define A's worst case from R, which includes R and all the games in the next round which remove A's chance for more points. A's worst case is the scenario where A gets no more points for the entire tournament, so A's worst case score is just equal to their current score under R. Since A's worst case removes all possible future point opportunities, any set of results containing A's worst case still gives A the same score as they had at R. On a fresh tournament, A's worst case would be the results of every first round game going the wrong way, resulting in 0 points for the entire tournament. Fun fact, getting 0 points in a March Madness bracket is just as difficult as getting a perfect first round. Finally, we'll define a complete set of results as a set that contains a result for every single game in the tournament. For March Madness, a complete set of results would have 63 elements, or 67 if you count the first 4, but no one counts the first 4. Even if only one game is undecided, it could go 2 different ways. Thus, every incomplete set of results has at least 2 complete set of results which contain it. We will find it useful to be able to talk about an arbitrary completed tournament containing a set of results R, so we will denote it as R bar. R bar represents one possible future of R and one way in which the tournament could be completed. We now have all the tools we need for the proof, so let's get started. First, let's see what I'm actually claiming. A can beat B if and only if A beats B under A's best case scenario. This lines up with the algorithm I showed you earlier. To proceed, we need to convert this into math using our new notation. First, we'll look at A can beat B. A can beat B is the same as saying there is some possible future where A gets more points than B at the end of the tournament. We can describe this with a complete set of results Q like so. But we also have to consider the results of the tournament so far R. To do so, we just simply add that Q must contain R, meaning that Q is essentially a possible future of R. As for the second term, A's best case is exactly best sub A of R, so we can rewrite this statement as A's score is greater than B's score under A's best case from R. This is now a lot more approachable to prove mathematically. Now we will prove each direction. We'll start by going right to left. We take it as true that A's score is greater than B's score under A's best case from R. Now we need to find some complete set of results which contains R in which A beats B. A's best case already contains R, so let's try to add results to A's best case which maintain the inequality. To maintain the inequality, we want B to gain as few points as possible, while A gains as many as possible. So let's consider B's worst case under A's best case from R. Since this set contains A's best case, we know that A gains no additional points in the added games. Similarly, since this is B's worst case, B also gains no additional points. Therefore, the inequality holds for this new larger set of results. This is still not a complete set, but it contains A's best case and B's worst case of smaller sets, so we know that additional results will not affect A or B's score. Thus, we can take an arbitrary complete set of results from this set and the inequality will hold. This is a complete set which satisfies A beating B and containing R, which is exactly what we needed. This is the harder direction, but really satisfying. We take it as true that there is a complete Q containing R where A has the higher score. We need to show that A's score is higher than B's at A's best case from R. We'll do this by step removing and adding results from Q to turn it into A's best case from R in a way that maintains the inequality at each step. Q is complete, so we first need to make it smaller. To make sure the inequality holds, let's only remove results which don't add to A's total. Let's also only remove results which come after R. So, our wanted subset S of Q is the results of R plus those not in R which give A points. These are exactly the results that are also in A's best case from R. So S is equal to the intersection of Q and A's best case from R. Using our addition property of score, we can rewrite this inequality in terms of A and B's score at this smaller set of results. Let's consider A and B's score at each of the results in this sum. Since R is not in A's best case, it thus gives A no points, so score sub A of R is 0. B's score from R may or may not be 0. We can then extend the inequality like so. We get that the inequality holds at the intersection of Q and A's best case from R. Notice that this set is a subset of A's best case from R, which we are trying to show this inequality holds for. Let's add results to get up to A's best case. Again, we can use our addition property. Moving around the terms, we can rewrite the inequality like so. Since R is in A's best case, A's score of R is positive. B may or may not have predicted R, so B's score of R may be positive or 0. Here, we can use our assumption that each game gives the same score for each bracket. Since A definitely gets this prediction right, A's score of R is greater than or equal to B's score of R. Thus, we can extend the inequality yet again. And cancel out the common sum. At last, we have A's score is greater than B's under A's best case. Exactly what we needed to complete the proof. A couple of years ago, my bracket was performing terribly. After the round of 32, I only had 2 teams left. I was so far behind my friends, I wondered if there was even a chance for me to still win, which kickstarted my investigation into this problem. When I started, I didn't even know if there was an easy solution, so it was very satisfying to discover the algorithm I showed you in this video. And not only was it possible for me to beat my friend, it actually happened. Just goes to show it's not over until it's over. There is still more to be learned about March Madness brackets. My algorithm does not help you if you are trying to see if a bracket can win amongst a group. With the 3 brackets on screen, it is possible for A to beat B and for A to beat C. However, it is impossible for A to beat B and C simultaneously, as no matter the result of this game, B or C gets enough points to beat A. I predict there is some relatively easy way to figure out if A can beat a group of brackets. I have not tried this problem, and I expect the solution to be a lot meaner than the one-on-one case, but who knows? I encourage you to give this problem a try. Good luck everyone, I've been Unanswered. Thank you for watching.